Hello and good evening, everyone. Welcome to the second lecture of Coordination Compound. Last day we have started off with this series where I will be discussing individual chapter for chemistry, and then we will solve the question for JEE Mains, JEE Advanced and Neet. So without further ado, let's start this classes. If you are present in the yesterday classes, let me give you a brief outline of what we have done. So the thing that we have done previously on class 1, first we have discussed about the introduction, in which we have discussed something about molecular or addition compound. Okay, there was initially two types of molecular addition compounds. First one was what? First one was double salt. Second one was our coordination compounds. We have discussed individual examples of double salt and individual examples of coordination compounds, and then we have also understood the difference between a double salt and a coordination compound, right? So it was the first thing that we have done. Then we have done something called, in detail we move on to coordination compounds, and then we were discussing something about the terms. We have discussed about the two terms. First one was central metal ion or atoms, and then we have discussed something about ligands, right? These two terms we have discussed. First one was central metal atom, second one was ligands. In central metal atom we have discussed that how this central metal atom is basically an electron pair acceptor, and hence it is basically a Lewis acid. And secondly, we have discussed that how these ligands are based nothing else but a electron pair donor. So ligands are electron pair donor, and therefore a ligand is a Lewis base. Then after that we went deeper into the ligands and we have discussed something called denticity. We have discussed what are monodentate ligand, also they are also called unidentate. Then we have something called bidentate ligand. Okay, first let me give you some examples of monodentate ligand that we have discussed. We have discussed something like ammonia and water, etc. Their name were amine and aqua. If you remember, AMMINE, amine is ammonia, water was aqua. Secondly, we have discussed bidentate ligands, also known as didentate. Over there, we have discussed something like ethylene diamine. Structures was something like this: NH2, CH2, CH2, NH2. Then we have discussed something: if someone has denticity more than 2, we generalize them by calling it polydentate ligand, in which we have discussed one particular ligand called EDTA 4 minus, that was ethylene diamine tetraacetate. Structures was something like this. Sorry. It was basically, we have discussed that it is a hexadentate ligand. It can combine with this one, the lone pair of nitrogen from this one, again a lone pair of nitrogen from this one, this O minus and this O minus. So it was a hexadentate ligand, and then it is also was a flexidentate ligand, right? Because it does not have to use all the 6 ligand, it can use 4 also, something like that we have discussed. So this was, and the last one that we have discussed was ambidentate ligand. Ambidentate ligand which have 2 binding sites but can use only one. Something like we have nitro NO2, in which there I have shown you nitrogen can act as a binding site, or we have ONO where same nitrogen but over here NO2 group, but here oxygen is acting as a binding site. So it was an example of an ambidentate ligand. Okay. So these are the things that we have discussed in the previous classes in the lecture 1 of this series, where we have discussed all these things from the introduction part to the coordination compound, and we move on to the details of the all the parts. Okay, I hope you have seen the video. If you have not seen, go back, watch the video. It will give you a lot of conceptual clarity, and it will help you to understand today's lecture in a much better way. So if you have not watched the first video, please go back, take some time out, see the video, and then come back to the second one. And if you are doing the revision, then of course you can see this video, or you can give a quick revision using 1.5x or 2x also the previous video. So without further ado, let's start off with today's class, and let me give you a brief of what we are going to do in today's class. In the lecture 2, we will be first discussing following terms, right? We will first discuss for the following terms, the terms like coordination number. Okay, and then the following terms like coordination sphere. Then moving on to the oxidation number, or we can call the same as oxidation state. Then we have to find out the charge of the complex ion. Then we have to find out again what are homoleptic and heteroleptic complex. And then we will move on to something called coordination polyhedron. Then after completing this, we will give you, or I will give you, a list of ligands. Ligands that are monodentate, bidentate, or polydentate. Okay, and then finally we will do the co sorry nomenclature of the complexes. So this is the outline for today's class, where we will start off with the terms and then we will move on to discussing the ligand's name, and at last we will complete it with various nomenclature or different type of complexes, and you will have a clear understanding of this. Remember, this class is very important in the sense that this class will give you a complete understanding about the basic concept of this chapter. This class is basically the foundation stone for coordination complexes, right? If you do this class, if you pay attention to this class, it all the basic concept will be clear. It is very important to clear the basic concept as we move further, so that you don't have any doubt for the basic concept, right? So you know that well. Put your pens and your copy notebooks ready. Just take the running notes, try to understand it, give a revision after you have complete watching the class, and let's go. Without on further ado, let's start off with the first one, that is coordination number. So what is coordination number? It is basically total number of monodentate ligand or double number of bidentate ligand, if any, that is attached to the central metal ion. through coordinate bonding, right? Basically, what is telling you what coordination number is, that is, it is the total number of monodentate ligand. It is the total number of monodentate ligand or double the number of didentate ligand that is attached to the central metal atom. Now let's understand this in a proper sense. Okay, let's say we take an example something like this. The thing that we have taken previously, FeCN6, let's say we have 4 minus. This was the compound. Now understand this. There is a central metal atom, that is Fe. Okay, this is my central metal ion. Each cyanide, if we see, each cyanide Cn minus can bond with only one atom, that is carbon or nitrogen, over here nitrogen. Okay, so each cyanide is having a coordinate bond with this iron Fe2 plus with the cyanide atom, right? So how many cyanide atom is directly attached to this iron? The 6 cyanide atoms, Cn minus, Cn minus, Cn minus, Cn minus, Cn minus, Cn minus. So now you can see that 6 cyanide atoms are directly attached to Fe2 plus. Fe2 plus has directly 6 Cn atom, that is forming coordinate bond. So what will be the coordination number? What will be the coordination number of this compound? Coordination number is 6. So total number of monodentate ligand, total number of monodentate ligands that is attached to the central metal atom or central metal ion. Okay, so over here the cyanide is a monodentate ligand. Cyanide is a monodentate ligand, and how many cyanide we have? We have 6 cyanide. We have monodentate ligand cyanide, and we have 6 of them. So it is basically a basically the coordination number is 6. Again, take a second example. Let's say we have something like this: CuNH3 whole 6 2 plus. Again, now we don't have to draw also. NH3 is a monodentate ligand. How many NH3 is there? There are 6 NH3. So the coordination number will be 6. Clear? Again, take another example also. Let's say we have Zn H2O whole 4 2 plus. We have something like this. So again, water or aqua, it is again a monodentate ligand. How many ligands are there? 4. So the coordination number will be 4. So all the examples we have taken, basically, we have taken the examples of monodentate ligand. Let's try out with some bidentate ligand also. I think you all are clear with this one. So now moving on to bidentate ligands, few examples. Let's say we have something like CO En whole 2 Cl2. Okay, En is basically a short form for ethylene diamine. Ethylene diamine is En. We used the short form En. So ethylene diamine, it is basically a didentate ligand. or bidentate ligand, whatever you want to call it. Basically, this is NH2, CH2, CH2, NH2. So it is attached by 2 points, right? So how many ethylene diamine is there? 2. And each has 2 binding points. So total number of binding points will be 2 into 2. That is 4. And Cl, that is Cl minus. Cl minus is a monodentate ligand. Okay. This is a bidentate ligand. So Cl, there are how many Cls are there? There are 2 Cls atom. There are 2 Cl atom. Each is contributing 1. So then it will be 2 into 1. This one is for En. This one is for Cl minus. So how many total we have? We have 4 plus 2. That is 6. So the coordination number of this compound is 6. Okay. So the coordination number of this compound is 6. Again, if you have understood this, let's try out with another example. Let's say we have a compound like this. Chromium, then something like this. Let's say we have something like this. The compound is chromium. Then there is 2 OX, that is oxalato, and bromine minus. Again, there are 2 ligands there. One is oxalato, C double bond O, O minus, C double bond O, O minus. This is my oxalato. Last day we have done this one. This is oxalato, right? And then how many binding site? It's a 2 binding site. It is a didentate ligand, or bidentate ligand. This is a bidentate ligand. Then we have Br minus. Then we have Br minus. This is basically a monodentate ligand. This is a monodentate ligand, right? So now again find out the coordination number. Try it on your own. Pause the video and try it on your own. Okay. Now I will do this. Coordination number is, how can we find out? First we have to find out the bidentate ligand. How many bidentate ligands are there? 2 bidentate ligands, and each has 2 binding sites. So 2 into 2, again same way like the previous example, and there are monodentate ligands. This one is a monodentate and there are 2. So the binding site is 1 into 2. 1 binding site and 2 is the number of ligands. So basically if we have done this, we will get 4 plus 2, so this is a 6. So the coordination number is 6 for this compound. Right? Clear? I think everybody has no doubt about this. How to find the coordination number we have done. For example, if all the ligands are monodentate, then simply the number of ligands is equal to the number of coordination number. Over here we have seen this. What we have seen is, see, NH3 monodentate ligand. NH3 is a monodentate ligand. So the number of NH3 atom that is present, that will be directly equal to the coordination number. So there are 6 NH3 atoms that are present, so the coordination number became 6. Similarly, water, again a monodentate ligand. Water is a monodentate ligand. So the number of water molecule present is directly will be equal to the number of ligands. So the 4 water molecules are present, so the coordination number becomes 4. Simple as that. If by chance there is a bidentate ligand present, like over here we have what? We have ethylene diamine. We have ethylene diamine, which is a bidentate ligand. This one is a bidentate ligand. So how many number of ligands, bidentate ligands that are present? So 2. So now we will do a 2 into 2. First 2 is for number of ligands. First 2 is for binding site, let's say, and then next 2 is for number of ligands. Then again we have, along with this, we have chlorine also. Chlorine is a monodentate ligand, so number of binding sites. So number of ligands is 2, binding site is 1. So again we will do 4 plus 2, so 6 is my coordination number. For oxalato, again this is a bidentate ligand, and bidentate ligand means 2 binding sites, and their number of ligands is 2, so 2 into 2, 4. We will have this one. Then along with this, there are bromine also present. How many bromine? 2 bromines are present. 1 binding site, 2 bromine. Just add up the total, we will get a 4 plus 2, and we have a 6. So the coordination number is 6. Clear, everyone? Okay. Now we will talk about coordination sphere. Now we are talking about something called coordination sphere. Now you have seen this, that whenever I write a coordination compound, whenever I try to write a coordination compound, I write it something like this: K4, FeCN6, or something like Ni, H2O whole 6, 2 plus, let's say, or let's say that vanadium CO6 minus. So everything, whatever we write for the coordination compound, this third bracket is compulsory. Each coordination compound contains a third bracket. So this part, that is the third bracket, which does not break further, this part is called the coordination sphere. Clear, everyone? This part which forms and does not break further is called coordination sphere. If you go by the definitions, it which central metal ion, central metal ion and the ligands, central metal atom and the ligands are directly attached and are enclosed in a square bracket. This enclosed square bracket is called coordination sphere. So basically everything inside the third bracket or the square bracket, whatever you want to call it, this part is called a coordination sphere. Clear, everyone? This part does not break further according to the present knowledge. Okay. Next one is our oxidation state. Right? Next one is called the oxidation state, or we can call it oxidation number also. Oxidation number also. It means the same whether we are calling it as the oxidation state or we are calling it as the oxidation number, both means the same thing, right? So now we will move on to what is oxidation state or oxidation number. Basically you have to calculate that. So oxidation state is basically calculated or basically found for the central metal ions. Okay, so for whom we found the oxidation state? Oxidation state is generally calculated for the central metal ion. And how we calculate it? It is basically the charge that is present in the central metal ion. Okay, so central metal ion, whatever the charge the central metal ion is carrying, that is basically the oxidation state of the metal ion. Now how can we find the charge? Basically it is calculated. It is calculated by using the charge of the ligands, using the charge of the ligands, as well as by using the overall charge of the compound. Okay, or coordination sphere. Anyone. For example, let's see with an example. Okay, now we have a compound, something like this. Let's say PtCl4 2 minus. Okay, we have a compound like this, PtCl4 2 minus. Now we have to find the charge of platinum. We have to find the charge of platinum, which will be the oxidation state, right? Now how can we find out? We can, let's take the charge of platinum as X. Clear? Now we have 4 chlorine. Cl has a charge of -1. Cl has a charge of -1. So overall there are how many chlorines? There are 4 chlorine. So we have 4 chlorine with a charge of -1. And the overall charge of this compound is -2. Now we will solve a simple math equation. X plus 4 into -1, that is -4, is equal to -2. Now when x -4, the -4 will move to this side of the equal sign. It will become +4, so it will be +4 -2. So x will be +2, right? So x will be +2. So the oxidation state of platinum, oxidation state of platinum in PtCl4 2 minus is how much? Is +2. Let's take another example. Let's say we have FeCN6 4 minus. Okay, another example in which we have FeCN6 4 minus. So now again Cn, let the oxidation state of Fe be X. We have Cn has a charge. Cn is basically Cn minus, therefore the charge is -1. So how many Cn we have? 6 Cn. So plus 6 into -1, and the overall charge is -4. So this one is there. So x plus 6 into -1 is -6 is equal to -4. Again, when -6 will move on to that side, it will become plus 6. So x equal to 6 minus 4. So x is equal to 2. So again the oxidation state of Fe in FeCN6 4 minus is plus 2. Okay. Now both of them we have taken basically an ion because there is an overall charge. Now let's take a molecule and find out oxidation state. Okay. Let's take up one molecule and find out what will be the oxidation state. Let's say we have something like this. CONH3 whole 6 Cl3. Sorry, my bad. Cl3. Okay. Now again we have to find out the oxidation state of this central metal atom. Central metal atom is this one. We have to find out the oxidation state. So now tell me, overall the molecule is 0. But if we break the molecule, let's say, what will be this one? CONH3. So this part, what will be the charge for this part? For the overall molecule to be 0, what should be the charge for this part? Cl, there are 3 Cl minus. 3 Cl minus. So the overall negative charge is minus 3. Overall negative charge is minus 3 because it is coming into 3 into minus 1. Chlorine has a charge of minus 1. So Cl3 chlorine atom has a charge of minus 3. So to be the overall molecule to be neutral, this part, the coordination sphere, has a charge of plus 3. Clear? Again I am explaining, understand this. Overall this molecule is neutral. Let's remove this one. Overall this molecule is neutral. Now we have to find the charge of this coordination sphere. We have to find the charge of this coordination sphere. We know that chlorine has a charge of Cl minus has a charge of minus 1. So 3 chlorine will have a charge of minus 1 into 3 because there are 3 chlorine, so minus 3. So if everything is 0, overall the molecule has no charge, overall charge of 0, neutral. So to balance this minus 3, this coordination sphere should have a charge of plus 3. So that is what we have found out like this one. So coordination sphere has a charge of plus 3. So CONH3 whole 6 has a charge of plus 3. Now find out using the same logic. Now one thing, ammonia is a neutral ligand. So ammonia has an overall charge of 0. So let's say the cobalt is X plus 6 into 0 is equal to plus 3. Anything multiplied by 0 is 0. So X is equal to plus 3. So what we have, basically we have the coordination number of, or the charge of cobalt over here is plus 3. Now I can understand that you might at this stage had some problem in finding out the charge because we don't know the charge of the ligands. Which one is neutral ligands? Which one has a charge of minus 1? Which one has a charge of minus 2, etc., etc. This is a common problem. But all you have to wait is 15 to 20 minutes. I will give you a chart which con- will contain lots of ligands. Some are monodentate with a minus 1 charge, some are bidentate with a charge of minus 2, etc. And that you have to remember because you have seen this one. If you don't know the charge of the ligand, you cannot find out the oxidation state of the metal, right? So for finding out the oxidation state, you need to know the charge of the ligand, which I will give you after some time. Okay, I will give you a chart-based formula, chart-based system where individual ligands, their structure, their name, and their charge all will be provided. Okay, so just for the sake of finding it for now, just use the concept that I have given. For example, I have told you ammonia has a charge of 0. So just for this time being, just do what I say. After you get the chart, you can do it all by yourself. And after few days, you just don't have to do so much calculation also. You will just see the compound and you will just calculate the oxidation state at your head. So something like that will come up. Okay. Then we will move on to the charge of the complex. We will move on to the charge of the complex ion. So the charge of the complex ion, basically a complex, can be three types. Basically the complex can be three types. Okay, a complex can be first be neutral, something like this. PT complex can be neutral. Overall, there is nothing outside, everything is inside the third bracket, and everything is inside the coordination sphere, and the overall charge of the coordination sphere is 0. So the complex is neutral. Okay, next one is when the coordination sphere is cationic. Basically, something like this. Example will be CO, NH3 whole 6, Cl3. Over here, we have seen in the previous one, the anion. This one has a charge of -3. So to balance this one, this part should have a charge of +3 because the overall the molecule is neutral. So cationic. So this coordination sphere is having a +3 charge. So whenever something has a plus charge, we call it cationic. Okay. So over here in this example, the coordination sphere is cationic. And the third one is, you can guess it right. Yeah. When the coordination sphere is anionic. When the coordination sphere is anionic. This also example we have done. Example like K4 FeCN6. Right? Now potassium. What is the charge of potassium? +1. So there are 4 potassium atoms. So the overall charge will be +1 into 4. So the overall positive charge is +4. So to balance this part inside the coordination sphere should have a charge of -4. So over here the coordination sphere is present in the anionic part. So now you can understand this. The complex are basically three types. First one, when the overall molecule is neutral, nothing is outside the coordination sphere and the overall charge is 0. Overall charge is 0. Next one, when the coordination sphere is in the cationic portion, because the coordination sphere overall has a positive charge. So the coordination number is cationic, or coordination sphere is cationic. And last one, when the overall charge in the coordination number or coordination sphere is negative. So over here the molecule has the cationic sphere in the anionic. Now, how this is different? Because the nomenclature will be different when the molecule is neutral and cationic and anionic. Okay. So after some time, you will understand this. So this is the charge on the complex ion. That can be overall, it can be neutral, it can be cationic, it can be anionic, something like this. And now we will move on to another very important concept, that is homoleptic and heteroleptic complex. Now understand this. Homoleptic. Homo means, everybody knows this, homo means same. Homo means something that is same, right? So what are homoleptic complex? Homoleptic complex are complex in which the metal ion is linked to only single type of ligand. Okay, metal ion is attached to only single type of ligand, means there are only one type of ligand. For example, CO H2O whole 6, homoleptic complex. CO NH3 whole 6, homoleptic complex. Fe CN6 4 minus, homoleptic complex. If the ligands are same, over here ligand is H2O, all the ligands, there are 6 ligands, 6 H2O. This is a example of a homoleptic complex. 6 ammonia attached to the metal ion. So, example of a homoleptic complex. 6 cyanides attached to iodine. Again, an example of a homoleptic complex. Now you can easily guess what will be heteroleptic complex. Let's do it with example. You will have something like this. Lot of example we have done. C2En2, Cl2, heteroleptic. PT, Cl2, Br2, 2 minus, heteroleptic. Because the ligands are of not the same type. The ligands are of different type. Over here, this is a one type of ligand, and this one is another type of ligand. Two types of ligand are there. Similarly, over here, this one is a one type of ligand, and this one is another type of ligand. So two type of ligands are there. It can be two, it can be more than two, it can be something which is more than one. It can be three types of ligand, it can four different types of ligand. Everything will fall under heteroleptic. Okay. If the ligands are same, then we have homoleptic. If the ligands are different, we have heteroleptic. And the last one is coordination polyhedron. What we mean by this? It is the, what do we call it? We call it spatial arrangement. It is basically a spatial arrangement of the ligands with the central metal ion. Okay, so basically, it is basically the shape of the molecule. It is basically the shape of the molecule. Okay, now we have, if you have done chemical bonding, we know that the shapes can be of different type. For example, something, if the metal is over here and we have something like this, let's say the ligand is something L, and then there is this one L, this L, this L. So this is a tetrahedral. What is the shape? Excuse me. The shape of this molecule is tetrahedral. Examples are methane. You have seen CH4, something like this. So basically, this is something like this. Again, there can be another shape also. If there are four ligand, a metal, and the four ligand will take place the four corners of a square. Something like this. This one is called tetrahedral. This one is called square planar. Then something can be like this, like a square planar. And then one is above, one is below. So if six ligands are there, this shape is called octahedral. Then there can be trigonal, bipyramid, and then square pyramidal, different ligands, different. How can we find the shape? We could find the shape by using VACPR theory, which we will learn after a few classes. Maybe after 3 to 4 lectures, we will learn about this, how to find the shape. So shape is called the polyhedron. We will find it when we will study VACPR. Then we will be able to find out the shape of the coordination compound. Okay. So right now it is basically octahedral polyhedron means it is basically the spatial arrangement of the ligands. Now we move on to the most crucial part of today's lecture, that is the ligands and their names. Ligands and their names and their charge. Very important because this is the base for your nomenclature. If you know this one, nomenclature will be just a cakewalk for you. It will be a 2 second job. And if you have if you don't know this one, then you will be losing marks, because in nomenclatures in boards as well as in competitive exam there is no two way. Either you are getting it correct or you are getting it wrong. You cannot have a middle ground in it. Okay, so without further ado, let's start off with the ligands. Okay, so the first one, or the first criteria in which the ligands are classified, are monodentate neutral ligands. Okay, so monodentate neutral ligands. Monodentate, as the name suggests, they had only one binding site. Neutral, so their charge is zero, and ligands. All are ligands. All are Lewis base, so they can give one electron. So the first one is NH3. The name of the ligand will be amine. A double M-I-N-E. Okay, so okay, the first thing first, everything will be in small letter. Okay, everything will be in small letter. So start writing it in the format A double M-I-N-E. So again, the charge will be zero. Next ligand is H2O. The name of the ligand will be aqua. AQUA. charge again 0. The next ligand is NO. We call it nitrosyl. Nitrosyl. Again the charge is 0. The next ligand is called CO, and we call it what? We call it carbonyl. Carbonyl. Again the charge is 0. Every charge will, we are talking about neutral ligand, so every charge will be 0 in this one. Okay. Then we have pH3. Okay. We have pH3. We call it as phosphine. Phosphine. Phine. Phosphine. Charge is 0. Then we have PPH3. PPH3 is basically we have three phenyl group, so we call it triphenyl phosphine. Triphenyl phosphine. Again, no charge, 0 charge. Again, we have O2. Then we have O2. We call it dioxygen. Dioxygen. Charge is 0. Then we have N2. N2 we call it dinitrogen. Dinitrogen. Again the charge is 0. And then we have CH3OH. CH3OH, we call it methyl alcohol, not methanol, methyl alcohol. No charge. Then we have CH3 NH2. NH2 is amine group, so the name will be methyl amine. Methyl amine, AMINE. The charge is again 0. And then we have NH. Then we have NH2. NH2CO. NH2, which is called urea. Charge is 0. Then we have CH3O, CH3, we call it dimethyl ether. Again, the charge is 0. And then we have CS. We have CS, we call it thiocarbonyl. When there is sulfur, we use the term thio. So its name is thiocarbonyl. CO is normal carbonyl, CS is thiocarbonyl. So this is the first set of ligands. All of them are neutral, all of them are monodentate. First one is amine. Remember this one. When there is only amine, NH3, we use double M. AMMINE. Amine. Okay, all other amine what you will see after this made by ethylene diamine, ethylene triamine, whatever it is, they all contain single M. Okay, the spelling are important. This is where the examiner will try to trap you, whether it is giving us double M or a single M. These are the small things, okay, that makes all the difference. So in H3 when it is given, it is AMMINE. Then H2O we have aqua, AQUA. Then CO is NO is nitrosyl, CO is carbonyl, PH3 is phosphine, PPH3 is triphenyl phosphine, O2 is dioxygen, N2 dinitrogen, CH3OH is methyl alcohol, CH3NH2 is methylamine, NH2CONH2 is urea, CH3O CH3 is dimethyl ether, CS is carbonyl, thiocarbonyl, sorry, CS is thiocarbonyl, S, whenever there is sulfur, we call it S. Thio is used to acknowledge sulfur. Okay, now we will move on to the next set, that is the anionic ligand. Okay, Let's start off with that one. Anionic monodentate ligand. As the name suggests, first thing you need to know, these are anionic, means they will have a charge, maybe -1, -2, -3, whatever it is. Anionic monodentate means they have only one binding site, ligands. Okay, so now you will see a trend in this, that in this, when there is an anionic ligand, either we add ido at the end or O, something like this. Let's say if we have F minus, we can either use fluoro or fluorido. Anything can be used. Charges -1. Cl minus, same logic. Chloro or chlorido. Charge will be again -1. Br minus, bromo or bromido. I minus, iodo or iodido. Clear? So everything will have a ido or O at the end. Then moving on, O2 minus, we have oxido. Either we call it oxo or oxido. If we have S2 minus, that is sulfo or sulfido. The charge is -2, over here the charge is -2. And then we have, let's say, OH minus. Normally we call it OH minus hydroxide. So similarly over here we call it hydroxo or hydroxido. Charge will be -1. Then we have something like O2 minus. O2 with a charge of minus. Okay, the charge will be -1. So we call it superoxido or superoxo. Superoxo or superoxido. Again, if we have O2 2 minus, charge is -2, then we have what? We have peroxido or peroxo, peroxo or peroxido, right? Now, if we have N3 minus, if we have N3 minus, we call it azido. We call it azido. The charge is -1. If we have N and 3 minus is in the charge, then we call it nitrido. Nitrido, the charge is -3. We have, let's say, something like NH2 minus. If we have something like NH2 minus, this is amido. Now see, over there only NH3 came to be amine. Okay, A double M. Over here, A single M. This you have to notice. Amido. With a O, we have a -1 charge. Then we have NH2 minus. This is called imido. Imine, imido. NH2 minus. Remember this, this is NH2 minus and this is NH2 minus. Okay, the charge is -2 over here. So this is imido. Then if we have H minus hydride, so hydrido. Hydrido with a charge of -1. So this is the list of your monodentate anionic ligands. Okay, from F minus is fluoro or fluorido. Chloro. Now when you are remembering this, remember this. You try to remember only one type. For example, let's say you are remembering is fluorido. So fluorido, chlorido, bromido, iodido, oxido, sulfido. So follow only one sequence. Don't get confused. Don't jump between the two sequence and get confused. Okay. So try this one sequence and go through this one sequence and try to remember this. So this is how it is. So first we have done the neutral ligands, monodentate neutral ligands. Then we have done the anionic monodentate ligands. So in the anionic you have seen we are adding O or ado. Okay. Then we have few, very few cationic ligands also. Okay. Cationic ligands are also there. Something like O2 plus. When there are cationic ligands, we use the term ium. When there is cationic ligand, we use the term ium. Like for Ido and O we are using for anionic, we call ium we are using for cationic. So it is called oxygenium. 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 Charges +1. Next one is NO plus. We call it nitrosilium or nitrosonium. Nitrosonium. Again the charge is +1. Then there is another one is NO2 plus. This is called nitronium. This is also +1. Okay. So these are the three cationic ligands that you need to know. Monodentate, they are all monodentate. Okay, let me write it down over here. These are cationic monodentate ligands. Okay, these are cationic monodentate ligands, and we use the term ium for this. And now the most important ones are the bidentate or polydentate ligands. Okay, now we are going to understand the bidentate ligand. The first one is ethylene diamine. Both the nitrogen has a lone pair. Both the nitrogen can bind with the metal via this lone pair. Okay, we call it ethylene di. Again, amine is coming, but not the NH3 one. A single one M. It is also called ethylene 1,2 amine. Sorry, 1,2 diamine. Okay, because two amines are grouped in the first present in the first and second position. So we give the sign En. This is the small sign for ethylene diamine. Okay, this is a very important ligand. Overall charge of this ligand is 0, so it is a neutral ligand. Okay, the next one, C double bond O minus, C double bond O minus can bind to the metal with 2 O minus. The name of this ligand is oxalato. Oxalato. Because again it's anionic, so O will come. Okay, oxalato. In short, we write it as C2O4 2 minus also. This is also written, and the short form is OX. The charge it has is minus 2. Okay, this is the second bidentate ligand. Clear? Next bidentate ligand is diphenyl. This one is there, and with this connected another pyridine link. Okay, this has a lone pair, it can connect with this metal. This again has a lone pair that can connect with the metal. It is called dipyridyl. Dipyridyl. DIPY. Dipyridyl. Okay, because these are basically nothing else but pyridine ring. This compound in organic chemistry we call it pyridine. So basically this is a dipyridyl, means this is a neutral ligand because both of them are does not carry any charge. So the charge of this ligand is again 0. So it is a neutral ligand. Okay. Then moving on, then we have a ligand something that looks like this. NH2 CH2 C double bond O O minus. Again it has two binding side. One is the lone pair of nitrogen, another is the O minus of oxygen. Okay. So this is called glycinato. Again a negative charge, so again O will come. Glycinato. Okay. In short form GLY, and the charge is -1. Okay. Moving on. CH3 C double bond CH3. We have this one. Again we have this name is acetyl acetonate if the complete molecule. So acetyl acetonate NATO NATO. AC is the short form. The charge is -1. Again due to the negative charge we have an O in this at the end. Okay. Then we have something like this DMG. This is called dimethyl glyoxymato. Dimethyl glyoxymato. Oxymato. In short form, we call it DMG. It has a charge of -1. Okay. So this is something like this. Now see, this bidentate ligands can also be classified in another way. Okay. Now the black ones that I have drawn, you can see that this bidentate ligands can be equally divided into two parts. This is one part, NH2CH2. Again, the same part is there, NH2CH2 is on one part. Okay, the same two equal parts are there. So this type of ligand that have the same part, we basically call them as AA type. AA type. Just remember this, we will use it in the future when we will be discussing isomerism. Okay. Again say this molecule CH2CO part is one part, and again there is another same part CH2CO minus. Okay. again the same part. So this is also an example of a AA type ligand. Again we are going, when we are going this way, then again we see this, there is a pyridine, this part, one pyridine group is in this part and one pyridine group is in this part. So again two same type of ligand, again this is also an example of AA type ligand. But over here you will see this molecule is not same. These molecules are not same. In H2CH2, let's say if we take this part, then we have this CO minus that is in the other part. Okay, so this is not the same. The two parts are not same. So these molecules are classified as AB type. This molecule are classified as AB type. Okay, all the blue molecules that I have drawn, these are all AB type because they are not equal. The two parts are not equal. So this acetyl acetinato is also an AB type molecule. This is also dimethyl DMG is also an AB type molecule. Okay. Just remember this, when the bidentate ligands can be divided into two equal parts, they are in AA type, like ethylene diamine is a AA type, oxalato is a AA type, dipyridyl is a AA type. And when the two ligands are not same, they cannot be divided into two equal parts. These are basically AB type, like glycinato is AB type, acetyl acetinato is AB type, and similarly dimethyl glycinato or DMG is also AB type. Okay. Now moving on to some polydentate ligand, we have discussed one and it's very important. I have drawn the structure previously also. Again, I will be drawing this one. NCH2 CH2 N. We will replace the hydrogen with CH2 C double bond O minus. All the ethylene diamine hydrogen of the attached to the nitrogen are replaced by CH2 C double bond O minus, CH2 C double bond O minus, CH2 C double bond O minus. This compound is called EDTA. Overall charge 4 minus. Full form ethylene diamine. Again single M, tetra means 4. There are 4 acetate group. Acetato. Why acetato? Because negative charge is there. So oxygen comes. O came. Okay. So ethylene diamine tetraacetate is the name of the molecule. It is basically a hexadentate ligand, but it is also a flexidentate ligand. Okay. This was the ligands, and the last type of ligand that we are left with is the ambidentate ligand. These are the most important type because with the change in binding site, the name also changes. So now we will start off with ambidentate ligand. Just a quick reminder, what are ambidentate ligand? Ambidentate ligands were basically two types of ligands in which it's a type of ligand in which there are two donor sites, but only one donor site can be used. Ambidentate ligands are those that have two donor sites, but at a time, but only one can be used. Okay, so let's start off. The first one will be our M C triple bond N minus cyanide. Over here, carbon is acting as a donor site. So when carbon is acting as a donor side, we call it cyanido. Okay, Cn. When something is Cn, we call it cyanido. Okay, Cn minus is cyanido. When the same thing, but nitrogen is a donor side. When nitrogen is a donor side, lone pair is being donated, we call it isocyanide. NC minus isocyanide. This is one. Okay, next one. Metal is there. We have O minus, single bond C, triple bond N. Over here, oxygen is acting as a donor side. Again, M plus is there. Not a plus, important. Metal is there, and then we have nitrogen lone pair, which is acting as a ligand, and C is there. Carbon and O minus is there. So again, same ligand, two binding side. One time oxygen is acting as a binding side, one time nitrogen is acting as a binding side. So when oxygen is binding as binding side, we call it cyanito. Cyanito, NaTO. Okay, or we call it cyanito O also. Okay, this one is called isocyanito, NCO, isocyanito, or we can call it cyanito N. Basically, this dash O or dash N is specifying the binding site. Okay, over here the first one is oxygen, so cyanato O. The next one is binding site is nitrogen, so cyanato N. So anything you can use, either you can use cyanato isocyanato, that also means the same, or you can use cyanato O or cyanato N also, that is also completely fine. So this one is another type of ambidentate ligand where both donor sites are there. One is oxygen, one is nitrogen. Sometime oxygen is being used, sometime nitrogen is being used. Okay, so we have another type, important ones. We have metal, and to this we have SCN, where sulfur is acting as a donor site. Again we have a metal, we have nitrogen lone pair that is acting as a donor site. Okay, when sulfur is acting as a donor site, we call it thiocyanate. Thiocyanate. Okay, or we can call it thiocyanate is also. Thiocyanate is also. This, you know this, we call it isothiocyanate. We call it thiocyanate O. No, sorry, N, because nitrogen is the binding site. So again, this is also a pair of ambidentate ligand where first the donor site is sulfur, the second the donor site is nitrogen, and the last, I guess, the last one of this class of ambidentate ligands will be metal is there, nitrogen, O minus. Over here, the lone pair of nitrogen is acting as a binding site. So, okay, the thiocyanate is SCN basically. This one I have forgotten. This is basically S. Whenever we write it SCN minus, it is thiocyanate, and whenever we write it NCS minus, it is isothiocyanate. Again, whenever we are writing this one, whatever, OCN minus, this basically means cyanato, and whenever we are writing, sorry, NCO minus, we are signifying isocyanato or cyanato N. Over here the nitrogen is the lone pair, so whenever nitrogen you are using, the nitrogen is acting as a donor pair, we call this nitro, or we can call it nitrito also, or nitrito N. Again, the metal is there, and we have O minus, where oxygen is acting as a lone pair, we call it, this one is only nitro, sorry, this one is nitro, or nitrito N, and this one is nitrito O. Okay, we can call this nitro also, there is no harm in it. Okay, so this one is nitro or nitrito N, this is nitrito or nitrito O, anything you can call it. Okay, this ambidentate ligands are quite important because a lot of thing comes in the exams. This show a particular type of isomerism also. So with this we will complete and conclude today's class. So just a quick revision of what we have done in today's class. We have first done with the things called terms, in which we have completed the terms like coordination number. We have completed what are coordination number. Basically we have discussed how this is monodentate ligand or bidentate ligand. If it's monodentate ligand, it is the number of ligands. If it is bidentate ligand, then we multiply it with 2, polydentate and something, so on and so forth. Coordination sphere we have discussed, that is basically, that is inside the third bracket, the things that are present inside the third bracket are the coordination sphere. Then we have oxidation number of the central metal atom. We have now learned how to calculate the oxidation number or oxidation state of the central metal atom. Now we have the ligand charts. Now you can easily calculate few of the oxidation number at your home also. Let's say we have fluoride minus fluoro or chloro. I know that the charge of this ligand is -1, or cyanide we have -1. If we have oxalate, it is -2. So using those chart, now you can easily find out the oxidation number of the metal ion. Okay, that is one thing. Then we have seen the charge of the complex. Charge of the complex can be overall, can be neutral. The coordination sphere can be in the cationic part, the coordination sphere can be in the anionic part also. Then we have seen what are homoleptic and heteroleptic complex. If all the ligands are same, then it is basically homoleptic. If the ligands are different, two or more type of ligands are there, then it is a heteroleptic complex. Then we have polyhedron. Depending on the shape, the spatial arrangement, how the molecule will look in space, that depends. That is basically polyhedron. It can be tetrahedral, it can be octahedral, it can be square planar. How we can find out this one? We can find out the by using VACPR theory, which we will study after that. Then we have discussed the chart. These are most important. What are monodentate ligand, whether it's neutral or negative. Then we have discussed bidentate ligands also. The bidentate ligands, AA type, AB type. The short form ethylene diamine stands for EN. EN stands for ethylene diamine. OX stands for oxalato. DMG stands for dimethyl glyoxymato. So these things are important. Polydentate ligand we have discussed, EDTA. And then we are wrapping up the today's class, because tomorrow the class that I will be uploading, the lecture, that will exclusively contain nomenclature. We will be doing the nomenclature of at least 20 to 30 compounds, different types of compound where the coordination pair in the cationic or anionic or whatever. And tomorrow itself we will be start doing the JEE and NEET questions, so that we will have a clear idea of how the questions are coming in the competitive exams. So that's all for today. I hope you have enjoyed the class. If you have any doubt, please put it in the comment sections. I will address it on the next day surely. And just keep learning, just keep your mind calm, just try to understand what is being taught, and just enjoy the classes. I will say, just as soon as you start enjoying the classes, all everything will be a cakewalk. Okay, monodentate, bidentate, this, that, everything will be a cakewalk once you start understanding and just start enjoying the classes. That's all you can do. So all the best for today. I hope you have done your notes and have a great time. So tomorrow we will be meeting with the next lecture. So adios for today.